For the first physics lab, we are going to observe objects under constant velocity using the momentum principle and Newton's second law. First, we need to know what the formulas are and what constant velocity means. In this case, constant velocity means that the total forces acting on the object are equal to zero by adding or canceling each other out. As you can see, the momentum principle formula is the change in momentum is equal to the net force times the change in time. It can be derived to the velocity form. The final velocity is equal to the initial velocity plus the net force divided by mass times the change in time. Since in this lab we're assuming that net force is equal to zero, then the mass will not matter. But the final velocity is equal to the initial velocity. To determine the position, we use the final position equal to the initial position plus the velocity times the change in time. On this video, my friend pushes the toy car, the system, towards the right, where the x-axis is positive. The point of origin is the middle or center of the toy car, after it has been released. By using tracker, I track the velocity from the time the toy car was released to a few seconds later. The axes are set on the toy car, and as mentioned before, the car moves on the positive x direction. The toy car started at origin 0, 0, and after being played for a couple of seconds, the final time is 0.767 seconds, and the final position is 0.495 meters. Before constructing the model in Python, we must determine a few things. The mass of the toy car is 0.034 kilograms, and by using the velocity formula, which is the velocity is equal to change in position divided by the change in time, we find that the final minus initial position is 0.495 meters, and that the final minus initial time is 0.767 seconds, therefore giving us a velocity of 0.645 meters per second. Once we have determined our values for the model, we can construct it on Python. We have set the value for the mass of the ball, the same mass as our toy car, 0.034 kilograms. The initial position being the origin, 0, 0, 0, and the velocity value is what we had determined previously, 0.645, 0, 0, in vector form. We will begin at time 0. Delta t will stay the same, 0.01, and we will change the CSV file name to car_motion.csv. Since we set the net force is equal to 0, we can say that the final velocity is equal to the initial velocity. Once we have arranged and organized our formulas, we can put it into our code. Once we run the program, we see the ball going in the positive x direction, and on the graph it shows a constant velocity in the positive direction. After gathering the data of the experiment from Tracker and collecting the data of the model from Python, we can compare them in a graph. The graph shows the plotted points in red representing the model, and the solid line in blue representing the experiment. We can see that the solid blue line and the plotted points are almost similar. The reason for the blue line being a little off is because we assumed there were no forces acting on it, when the toy car was actually interacting with Earth's gravity and the floor's friction. Now we will answer our questions. What if we change the axis, where the positive direction is toward the left of the x-axis? We can go back to Python and test it. To test this, we will set the velocity to a negative velocity. Once we run it, we can see that we have the same graph, but with a negative constant velocity, and the ball goes in the negative x direction. What does it mean? This means that if the total force acting on the object was not equal to 0, then the velocity will not be constant. To prove this, we can go back to Python and change the net force vector. In this case, we change it to 2, 9.8, 0, making the x component be friction acting on the object and the y component Earth's gravity. If we run it, we can see that we don't have a constant velocity, but a change in velocity over the change in time. This concludes the analysis of Lab 1. I hope you learned about Newton's second law and the momentum principle, and I hope you liked this video.